All right, so very happy to have Peter Scholze delivering the last talk of the conference.
Thank you. So, it's my pleasure to give this final talk, and I didn't know what I will talk about on the first day, and now I know even less what I'm talking about. So, maybe the question I want to answer in this, or not answer in this talk, is like, where do we go from here? And I guess the correct answer is to the party. So maybe I shouldn't talk for too long. But more mathematically, I have the feeling that so far this kind of field of perfectoid spaces, if one may call it a field, was mostly, like the directions it was taking were mostly determined by the kind of questions that the people in the field have been working on before. So, for example, some of the stuff that you've heard about in Jared's and Kieran's talks about diamonds and so on, that's very much motivated by some project of Laurent Fagenmine, and which eventually deals with local lengths over periodic fields. But both Laurent Fagen and I worked on local lengths over periodic fields before we started perfectoid spaces, and so I don't think there's an inherent reason that one should use perfectoid spaces to study it. It's rather that it's something we are familiar with, and thus we started to use perfectoid spaces to study the local length correspondence over periodic fields. And so one could give, well, maybe people asked me here whether it would be interesting to apply perfectoid spaces to toric varieties, to I don't know what, to periodic multiple zeta values, to whatever. And probably it is. I have no idea. I don't know these other subjects. You should figure it out. In particular, like if you have the feeling that, you don't have to understand everything that's been going on in this week. Maybe there is some concrete thing that you learned this week, which you think this might be helpful for me, and you should maybe pursue whether there's something in the theory that helps you in your stuff. And right, so for example, I think something quite exciting that happened recently is, or maybe before I come to this, let me say that when I gave one of the first talks about perfectoid spaces, it was in Princeton in 2011 at a workshop. I think I was expected to say instead something about local Langlands, and so anyway I gave this talk, and this was a local Langlands day. And after the talk, Jared Weinstein was speaking, and Jared Weinstein was just in the course of trying to understand what would be Lubin-Tate space at infinite level, and he could write down equations for it, but he couldn't give this space a geometric structure. And so, like this first application there of perfectoid spaces was just because suddenly, right after my talk, there was this guy who needed perfectoid spaces. So, okay, so it's unclear where this field is going, and you should try to figure it out yourself. So, as another example, Yves André has recently used perfectoid spaces to prove the following theorem, formerly known as the direct summand conjecture. Which was formulated by Hoster in, I think, 73. So it's rather old, and I think it was quite a focus of work in commutative algebra. Which says the following, and on the face of it, it seems to have nothing to do with perfectoid spaces whatsoever. It's just a very classical commutative algebra question. So if you have just any regular ring, and you have a finite extension of this regular ring, R into S is a finite injective map. So say you take an extension of the fraction field and you normalize R in this extension. Then the conjecture says that this map will always split as R modules. All right, that's the theorem. Why is it interesting? Well, for one thing, it implies that this map is what's called pure, and this means that you can actually do descent along this map. So, oops. So you get some non-flat descent property for any like such regular ring, which is quite nice. It's also it's a part of a landscape of conjectures called Hoster's homological conjectures. And I think they are being solved by the minute, more or less. So I asked a few people, and they seem to have more and more of these conjectures. No? So this result of Andre was refined by Bargev, who proved the derived variant, and I think Lingshu Ma is working on this called Schwede, and I'm probably forgetting others that I should name. If you don't tell me, I cannot write them. And they're using this stuff to develop some purely commutative algebra theory. So develop some theory of, I think it's called test ideals and mixed characteristic. Right? That's cool. Perfectoid spaces also started to appear in completely other areas. So there are also some connections to algebraic topology. Via something that's called topological Hofschild homology. So, I mean, this gives me an opportunity to actually say a little bit about the history of these. This paper of Bargott Butt, Matthew Morrow, and mine on integral periodic Hodge theory. So this actually started in discussions with Matthew Morrow about topological Hofschild homology, and we tried to understand the topological Hofschild homology of such schemes over OC, because we had the feeling that there might be something interesting there. And so, in thinking about this, at one point we realized that there should be this cohomology series that we eventually constructed without any of this topological machinery, but which some of the topological machinery is very much the motivation for this. And so far the connection hasn't been worked out, but might also be an interesting avenue. So also, Jacob Lurie I was speaking to Jacob Lurie a lot this week, and he had some very fancy reinterpretations of this thing that I don't want to even, I would say the wrong words. And a lot of people have used perfected spaces in, for me, unexpected ways. So Shinatori proved something about closed local fields this way. Alberto Vezzani proved something about rigid motives, and a lot of other people did different stuff. And so, as I said, but I wanted to come back to things that I'm familiar with. So, as I said, Laurent Farge and I, we both worked on local lengths over periodic fields. And so I want to a bit explain about this program about diamonds and Stukas and so on that came up in Jared's and Kiran's talk. I want to explain a little bit about this. So. Yeah, but for the rest of the talk, let's concentrate on this program of these mixed characteristic Stukas. All right, so maybe I should give some kind of background. How did Stukas historically come up? So Stukas came up in the situation of function fields. So really Stukas are a function field thing. So let's say, and function fields are the same as curves, so let C over FQ be a projective smooth, say geometrically connected curve. See, I don't know what I'm talking about, so I have to try to find a page where I've written something like this. Okay. So if you have a modular space, so I don't want to say much about what a Stuka is. I want to tell you how the modular spaces vaguely look like, what kind of structures they are. So if you have a modular space of Stukas over C with one leg, I should have said that, first of all, I also have G a reductive group. Let's say it's also defined over FQ for simplicity. So you don't really lose much if you just assume that G is GL2. Actually, this was a very case where Drinfeld first introduced these ideas, and then they were subsequently generalized by Laurent Lafort, by Warshawski, and so on to general groups. So you have this modular space of Stukas with one leg, right? So, so what's a leg of a Stuka? A leg of a Stuka is just a point of the curve where something happens. So if you have a modular space of Stukas, and particularly Stuka has a leg, which is a point of the curve. And so by just forgetting all information about the Stuka except where the leg is, you get a projection map to the curve. So you have a map F from the space of Stukas, and I should put many decorations here, mapping down to the curve. All right? And so, in particular, if I look at, so I should say this. So this is the analog of Shimura varieties. So Shimura varieties are maybe modular space of certain BM varieties with X structure, something like this. And at least in the presence of good reduction, you can define good integral models of these which live over the spec Z. And so the analog of spec Z in the function field case is, of course, this curve. So, all right. And so if you look at the push forward, some of the cohomology of this Stuka, but not the absolute cohomology, but some of the relative cohomology. So you push the sheaf QL bar, you push it down to the curve, and what kind of structure is this now? This is now a local system on the curve. So in other words, it becomes a representation of some more fundamental group of C. Another way to think about the fundamental group of this curve is that it's the unramified, everywhere unramified quotient of the absolute Galois group of F. And on the other hand, this is some kind of, you should think of this as the analog of the cohomology of Shimura varieties. And at least if you somehow take a direct limit over all levels, this becomes a representation of some adelic group. A is the adels. I should have said, right, so F is a function field of C. And A are the adels of F. So this restricted product of all the local fields of F. And so this way you get these representations which are simultaneously the representation of this adelic group and of the absolute Galois group. And so these are quite interesting because they realize Langness correspondences. So the theorem in the n equal to 2 case probably to Drinfeld, and then Laurent-Laforgue has some theorems and other people, is that if you look at these guys, then they decompose into the direct sum of certain so-called automorphic representations pi of this adelic group of this representation, and then you tensor it. So you isolate the pi isotypic component in this guy, and then if you take the pi isotypic component, you still have the other group acting, the Galois group, and so these sigma pi's are representations of the absolute Galois group of F, which maybe in the setup I'm considering are unramified. There are few details wrong in exactly how I'm writing this down, but I only mean to give an idea of what's going on. And so this association from automorphic representations of this adelic group to Galois representations defines the global Langness correspondence in some cases. This pi is not so nice. Unfortunately, it doesn't do so for all representations. And it was a very clever insight of Drinfeld that you could get all representations if you looked at these modular spaces of Stuka with 2 legs instead of 1 leg. It's spaces of Stukas. It's 2 legs. All right, so how do they look like? Right, so as I said, if you have a Stuka with 1 leg, then just remembering the leg gives you this projection to 1 copy of the curve. But if you have 2 legs, then you get 2 points on the curve. In other words, the point on the product of the curve is itself. So in the 2-leg situation, the situation is instead that F is a map from the space of Stukas. And again, I should write many decorations here. If you read Vincent Laforgue's recent papers, they have like 5 downstairs and 7 upstairs or something. Now it projects to 2 copies of the curve. Okay? And so let's say I just order the legs. I'm always free to just choose on ordering my modular problem. Actually, it's necessary to order them because you ask slightly different conditions. It's different legs. Okay, so now let's try to do the same thing. Let's try to do push forward QL bar. Actually, for the experts, I should put a lower shriek there, not a lower star. And there are many of these issues that I'm completely glossing over. It's again a representation of the adelic points of your group. But what's the fundamental group that's acting? You would think that now you get acting the fundamental group of C times C. And as Kiran said, the fundamental group of C times C is very different from two copies of the fundamental group of C. For two reasons in this case. One reason is that even if C was not a curve but just a point fq, then C times C is still fq, so it's pi1 is Z hat, it's the Galois group. On the other side, you have two copies of Z hat. So, okay, that's kind of stupid, but also if you work over an algebraically closed field, if you work over fq bar, it wouldn't be true. But a clever realization of Greenfeld is that actually there's a small extra structure on the space of Stukas called the partial Frobenius, which allows you to regard this as a representation actually of a pi1 of C times C, where you mod out by phi to Z in some funny sense. So a concrete way of saying what this pi1 is would be to say that it classifies finite État covers of C times C together with a lift of the Frobenius on one of the copies. And if you do the slight modification, then actually this becomes isomorphic to this product. And so that's what is known as Greenfeld's lemma. And I think it was this consideration of the cohomology of the modular spaces of Stukas that led Greenfeld to discover this lemma here. All right. So, okay, so that's, I think, as much as I wanted to say about the function field case. Let's see what I have written here. No, it was not. Because I wanted to say what this looks like. So, again, theorem of the same people is that now basically for good choices of data, you certainly get all cuspidal pi. You get all the ones you want. And so now it's a representation of a product of three groups. And so the first part is this representation pi, and then it's paired maybe with sigma of pi, and then maybe with a dual of pi, where both of these are representations of pi. Get something like this. And so this way one can define, get a global Langlands correspondence. For, well, the first case was GL2 Greenfeld, GLN by Laurent Laforgue, and NEG by Vincent Laforgue. All right, so I think that's what I want to say about the function field case. Okay, so obviously we would love to do the same thing over number fields. And I mean, we have our modular spaces of Shimura. We have these Shimura varieties. So which are analogous to spaces of Stukas with one leg, and we can get a lot of the Langlands correspondence from this, but we've somehow exhausted what we can do there. And it would be great if we would have a modular space of Stukas with two legs or something like this, which would give us a rest. But there's an obvious problem. What is the analog of C times, and here I should write C times of Q, C. And so you would want something like spec C times spec Z, and it should be a surface, and of course nobody has any idea whatsoever what this should be. Okay? And so here enters the magic of diamonds. We can make sense. Well, maybe not of spec Z times spec Z. People usually write something like F1 if they are talking about this business. But at least of something like spec QP, or maybe even spec ZP times spec F1, spec QP. Or even spec ZP. So in a sense, you can make sense of the completion of whatever this hypothetical space is if you complete at the point P, comma P. Or maybe I should also write spiff somewhere. It's so vague, this discussion, that maybe these details also don't matter. So, more precisely, namely, we can take the product spotty QP times spotty QP in category of diamonds. And get something two-dimensional. So let's actually try to do this. How does this work? It's a quotient. So we write one copy, say, as QP cyclotomic modulo this action. Then it's the same thing, because spar D for such a diamond is just spar D for the tilt, modulo the specific action of ZP cross here. And actually, that's the same thing as taking, so this is like a punctured open unit disk, like a Perfectoid punctured open unit disk. And if you take the product of this QP, you can check that you actually get the same thing as the diamond associated with the analytic adic space, which is a D star QP. So that's a Perfectoid punctured open unit disk. And still, we need to divide by an action of ZP cross. Okay, so that's what QP times QP is. It is this Perfectoid. Like one QP copy is very easy to see because it's the base, and the other QP copy got into this funny Perfectoid open unit disk, which you need to mod out by ZP cross. No, I don't need that, but I need a diamond somewhere, right? Yeah. Thanks. And okay, and now there's an analog of Drinfeld's lemma here. The following theorem, which you can find in the paper of Jared Weinstein, which tells you that if you look at the fundamental group of this spotty QP times spotty QP, and again you mod out by one copy of Frobenius on one of the sides, it obviously doesn't matter which side you're taking, then it's the product of the spotty QPs of these copies. But this is really just, as one would expect, the fundamental group of this diamond is just the absolute Gara group of QP. All right, so that's pretty closely resembling Drinfield's lemma. And so how much time do I have? 20 minutes or something still? 20? Good. Yeah. Right, so I wanted to explain this result in terms of this perfectoid open punctuated open unit disk. So equivalent assertions are that if you take the fundamental group of this perfectoid open unit disk and you model out not just by ZP star, but you also take into account this Frobenius. And if you take the two things together, you somehow get a quotient by QP cross, where this is somehow really the same as ZP cross times phi to the z, where the phi corresponds to p. So the diamond associated with this quotient is the same as this diamond here. So it's equivalent to saying that this is two copies. Two commuting copies of the absolute Gara group of QP. Or yet equivalently, so it's easy to see how one copy of this absolute Gara group arises here. It's just the copy that you get from the base field. So if instead you look at the same object but over an algebraic closure of QP completed. So you take this perfectoid open unit disk, punctured open unit disk over this algebraic closed field and mod it out by QP star in some sense. It makes sense as pro-Ital sheaves. That this is the same thing as the absolute Gara group of QP. And maybe let's stare at this statement for a second. What does it do? So on the right-hand side, we have the absolute Gara group of QP, which is manifestly an arithmetic object. Whereas on the left-hand side, we have some kind of funny geometric object, but it's defined over CP over an algebraically closed field. And so it identifies the absolute Gara group of QP with something geometric, something defined over an algebraically closed field. It's kind of funny. All right. So I think that's what I wanted to say about Drinfield's lemma. And so now let's go to modular spaces of Stukas. I should say that in the first half of the talk, I was talking about global function fields. There's some kind of analog of this global story of function field over local function field, so FP Laurent series T. And I'm now passing to the local setup, but also now passing to QP, to some mixed characteristic. All right. So you have them as one leg, so you have some space of Stukas living over spotty QP. And so these actually turn out to be, for the most part, objects that are actually known. So these turn out to be generalizations of what I call Rutherford zinc spaces, which themselves are local analogs. I mean, local in the p-adic sense. Analogs of Shimura varieties. As one would expect from, like, the kind of philosophical comments I was making. So maybe let me give one example for what these things look like. Somehow coming back to these Lubin-Tate spaces that Jared Weinstein was considering. So, and that also came up in Anna's talk at the end. So this Lubin-Tate spaces situation is the following. So there you start with, let's say, some H, which is a one-dimensional formal group of finite height, of some height n. As such, it's also a p-divisible group. So there is some kind of equivalence between certain p-divisible groups and certain formal groups. And this H lies in this category, which you can both consider as a formal group and as a p-divisible group. Yeah, so these Rappaport Singh spaces in general are modular spaces of p-divisible groups, and I want to give just one example of how they look like. So you look at the deformation space of H. This turns out to be, let's call it MH. This turns out to be, let me call it frac H. This turns out to be this non-canonically isomorphic to the formal spectrum of the Witt vectors of Fp bar in n minus 1 variables. So if n is 2, that's just one variable. And so then you can take the generic fiber. Let's call this now MH. That's an n minus 1 dimensional open unit disk. And there's a whole tower then. MH1 to MH0, which is just MH, where MHN classifies isomorphisms between, I need to give some name to the deformation. So that's the deformation space of this one-dimensional formal group, and I need to give some name to the universal deformation. Let's call it script H. N was already taken. Okay, so where H is it? Universal deformation. Okay. So this is a p-divisible group of height n, so this means that the p to the m torsion characteristic 0 which should be isomorphic to the sky, but not canonically so. So you can classify all the possible isomorphisms. And so if you take the whole inverse limit of this guy, actually I need to write this funny similar to, in the inverse limit this becomes a perfectoid space. Okay. So this is something which you can find in my much more generality in my paper with Jared Weinstein. And in a very explicit way, you can find it in Jared Weinstein's paper on the modular curve. So he gives you explicit equation for what the space is. It's really amazing. So it's really funny. So you can't write down explicitly what these finite level spaces are, but you can write down explicitly what the infinite level space is. So in some sense, the infinite level guy is simpler than all the finite level guys. Right. What do I want to say? Right. I want to state the following theorem. Again, from my joint work. So if C over QP is an algebraically closed complete extension, as usual, then one can actually classify the C-valued points of this infinite level Lubin-Tate tower. And to state it, well, let me use this notation in case there have been too many x's already. Let this be the Falk-Fontaine curve corresponding to the tilt C flat. So recall that to construct the Falk-Fontaine curve, you need some perfectoid field of characteristic P. You need to take C flat. But then because you started with something characteristic 0, this comes equipped with a canonical point infinity corresponding to the chosen untilt C. All right? Then if you compute the C-valued points of this guy, this turns out to be something rather explicit in terms of the Falk-Fontaine curve. It turns out to be just injective maps from this trivial vector bundle O of n, O to the n, into another rank n vector bundle, which is called O1 over n. So this is of rank n and degree 1 and is semi-stable and is unique with these properties. Another way to think about this, where this comes from in our case, is that it comes from the Dieudonné module of this one-dimensional formal group of height n. Okay, so it classifies such injective maps. I don't think I've used F here, so let's call it F. Such that the co-kernel of F is supported at infinity. Okay? So that's maybe a priori rather surprising, because on the left-hand side we have something which deals with p-divisible groups. On the right-hand side we have something which doesn't mention p-divisible groups at all.
So this is an n-dimensional thing going into a one-dimensional?
No, right. O1 over n is the domain. The rank is the denominator. These are not line bundles in general. So these are of this. So the co-kernel must always be a torsion thing of dimension 1 somewhere at this closed point. And so you ask that this happens at this point infinity. Okay, so starting from there, you could reinterpret all of these Rapport-Singh spaces as completely in terms of vector bundles on the Falk-Fontaine curve, and slowly somehow everything was translated into this other picture. And then again, these vector bundles on the Falk-Fontaine curve have been reinterpreted as some kind of Stukas. So this can also be said in terms of Stukas. And these are Stukas in a sense with one leg at this chosen until infinity. Okay? But now, in the world of diamonds, we can forget all restrictions about having just one leg, and so there is no obstruction to considering moduli spaces of Stukas with any number of legs. Namely, so what are our test objects? So if you want to write down a moduli problem, you should first say what the test objects are. And so the test objects are the elements S in this, what was called PFD, which were the perfectoid spaces of characteristic P. And legs, these legs are at, well, maps to our curve. Our curve in this case is body QP. So the legs are at points, at S-valued points, x1 through xn. Yes, this body QP of body QP. So it makes perfect sense to have such a perfectoid space in characteristic P and give it multiple structure maps to body QP. So these correspond to recall that giving such a structure map to body QP was the same thing as giving an untilt of S. And so now we don't just have one untilt, but we really have n untilts of S. And so now we had this ys, which was in a sense S times spar QP, something like this. So it's at least true on diamonds, and which was in a sense fibered over S. So at least there was a map of diamonds. But then you had these sections which were closed immersions and really of adic spaces now. And in the sense, the tilt was the same thing as S, but maybe only the associated diamonds are really the same. So in this sense, these like you should think of these closed emergence as some of the graphs of the structure map to body QP. Okay, and then one can consider essentially consider phi modules over this ys, or a small extension of it, or compactification of it. So actually, Stukas are defined over a slightly different space, which corresponds to the product with ZP here. With poles or zeros. So this phi is not everywhere in isomorphism. It might have some poles and zeros, and these poles and zeros are at the xi. At the closed at these closed subschemes of ys, which are certain divisors in ys. Okay, so it's a notion that makes sense, and so you can talk about these. So you have these analogs of these maps. So you have the space of Stukas, again, with lots and lots of decorations, mapping to two copies, say, of Spidey times Spidey QP. And then again, you can try to look at the cohomology of the space of Stukas. In the local cases, we'll now get an action just of the periodic group G of QP. And on the other hand, you will get an action of the pi1 of this diamond. But for the same reason as in Drinfeld's original setup, you actually get this extra partial Frobenius, which allows you to identify this with, by the Drinfeld lemma, with two copies of the absolute Gamma group, QP. And the hope is then that we can just mimic, for example, what Vincent Laforgue has recently done for any reductive group, and thus define a local Langness correspondence for reductive groups over periodic fields. And I think I need to stop.
Questions?
So is this a thing that's actually completely worked out now? Do we know how to get the, for NEG, get the local Langlands in this setting?
It's not worked out yet, but it's being written. I don't see too many obstructions.
Does one ever need more than 2 legs?
Does one need more than 2 legs? GLN is probably anyway done for local lengths, but anyway. No, for a general reductive group, something like E8 or something, I think you need a lot of legs.
Any other questions?
Oh, just want to ask how should the homology enters into the picture in the beginning of the talk? You said you want to establish some connection or something, but did not elaborate on it.
Okay, the question was, what does topological Hochschild homology have to do with any of this? So this was started through a theorem of Hesselholt. That so there is a theory called topological Hochschild homology, and you can apply it to the ring of integers in our complete algebraically closed field. Say you maybe also p-complete this guy to get rid of some junk. And then this guy is a spectrum which has an S1 action. You can take the homotopy fixed points under this S1 action. And then you can compute all homotopy groups, but let's consider, say, on the simplest, which is a connected component. So that's some ring. And this ring, is A-inf. So that's how Hesselholt thinks about A-inf.
Okay.
And I don't know, I mean, there's a lot of structure on this topological Hochschild homology. So, for example, it also has a Frobenius. And and also if you have something over OC, then it should be, whatever TH8, applying the similar construction to a scheme over OC, should certainly produce a module over A-inf. And it also has a Frobenius. So you get some A-inf modules with a Frobenius. And so that's essentially the cohomology theory we're constructing.
All right, well, let's thank Peter again. And maybe just let's thank all of our speakers once more for a really fantastic series of lectures.
Yes.
And we're looking forward to the student presentations tomorrow.
And we thank the organizers for a wonderful job. It was a wonderful experience. All the organizers.